Hello. So we will review the hypothesis testing framework. And in here, we are going to consider hypothesis testing for the population mean. Before talking about this, you may remember how the hypothesis testing proceeds. It is not a kind of neutral way of inference, but you need to have a kind of belief of your hypothesis even before looking at the data. So, and because we are only considering the population mean, it means the hypothesis is stated in terms of the mean. So, for example, there are three different types of hypotheses. First, you believe that the hypothesis is, so a hypothesis is stated this way. You believe that the population mean equals to something mu y0. We add 0 after the subscript because it is your belief. It is not the true value, or it is not from the data. It is just your belief. There is no reason for that. So it is an unfair way. You already have a belief, and you have alternative hypothesis, which may be inequality or just negation. So you may, in the first case, it is called one-sided test, upper tail test. That is, you believe that the true population mean is mu 0 or smaller than that. Versus, if you are wrong, alternative hypothesis is that the true population mean is strictly greater than mu 0. So in that sense, it is one-sided. For example, I believe that the average GPA of those who watch this video is smaller than 3.5. I believe your average GPA is smaller than 3.5, but if I may be wrong, it's my belief, I don't have the data. If I'm wrong, the alternative is that the true mean is greater than 3.5. So those value is just a number. Or like you can put it this way. You may believe that the true population mean is mu 0 versus, if that is wrong, you are going to switch to the belief that the mean is strictly smaller than mu 0. So for another example, so I believe that the expected value of tomorrow's stock return of my portfolio is greater than, say, plus 2% point. I believe that my stocks will grow like more than 2% tomorrow or next week, unexpectedly. If I'm wrong, I am going to switch my belief to the case that the hypothesis that the true mean is strictly lower than 2% point. The expected return is strictly lower than 2% point next week. So this is lower tail one-sided hypothesis testing. Or you may just consider both sides. I believe that the average income for a randomly chosen household is say like $50,000 last year. It may be underestimating or overestimating. So if I'm wrong, the true parameter would be just different from 50,000. Could be greater than that, could be lower than that. So both sides are open, so it's two-sided test. I believe you have heard about them. So now I'm reminding you of these terms. And by the way, H0 is called the null hypothesis because H0 is believed throughout the process, throughout the inference procedure, unless it is rejected. And H1 is the alternative hypothesis, which will be true if your H0, your null hypothesis, is wrong. So there are the names. And the most difficult, the most confusing term in statistics, p-value. No one understands it correctly. P-value is defined as the probability of drawing a test statistic, for example, sample mean, at least as adverse to the null hypothesis as the value actually computed with your data, assuming that the null hypothesis is true. The definition takes 3 lines. I'm not sure if you could understand this. Let me talk about this. So suppose that there is a coin, and I believe that a coin is fair. There is a coin. Suppose that there is a coin which is fair, which I believe fair, but it may be unfair. So then what I can do here is I'm going to test my belief that the coin is fair. Then I'm going to throw the coin 100 times. If I get 50-50 out of 100 coin tosses, then it's simply fair, right? However, suppose that what happens if I have 51 heads and 49 tails out of 100? Even though it is different from my belief, but still that's likely. That is likely outcome under my belief. Even if my belief is true, even if the coin was fair, still you may get 51 and 49. That's also possible. Then what if connect then 52 and 48? Still that's likely. And if you go away from 50 to this side or to the lower side, so as you go out of 50-50, out from the 50-50, then the result will become less likely to happen. So for example, if you think about you get 99 heads and 1 tails. Can it happen? Of course not. This is what it says, adverse to the null hypothesis. So if you have 99 to 1 as a result, that means it strongly contradicts your hypothesis, your null hypothesis. So then what you have to do here is, okay, but theoretically that is possible. Theoretically, there is a very small probability that you get 99 heads and 1 tails, even if the coin is fair. Still, that's possible. Just the problem is the probability is very, very small. So we have to cut at some certain probability threshold. So that's the significance level. Significance level is a pre-specified probability that if the probability of observing this outcome is lower than 1%, for example, if you set the bar as 1%, if the probability of observing 99 heads and 1 tails is lower than 1%, then I cannot believe this, right? This is so unlikely that I think the coin is unfair. I'm going to reject my belief, which was the coin was fair. So that's the significance level, and that's the concept of p-value. So p-value is, if we consider two-sided test, the p-value is considered this way. First, y bar minus mu. So remember, think about this. Y bar is what the data tell you. This is the observation from the data. Say in our example, this is the probability from 100 coin toss, and mu y0 is my belief. I believe the probability of head is 50%, but from 100 coin toss, you may get 50%, but also you may get 99%. That is possible. Any value between 0 and 1 is possible. And you observe one value, right? So when you throw 100 coins, 50-50 is possible with certain probability, and say 90 to 10 is also possible with a different, maybe small probability. So out of those probability distribution, you draw one outcome. So you actually throw 100 times and calculate the observations, calculate the observed sample mean, and that is Y bar ACT, actual realization. Suppose that your actual realization is 90 heads and 10 tails. So you got 90% probability of heads from your data. Then, how extreme is that? Okay, or if you may think about 80 heads and 20 tails. It's still extreme in some sense, but 80 could be not that extreme. I don't know there. So you must set the threshold that is calculated by this probability. So suppose that you observe 80% of heads, then I would calculate what is the probability that you actually observe. You observe sample average greater than 80% or lower than 20%, because lower than 20% is equivalent to observing greater than 80%, equally likely errors and of the same size error. So if you could calculate that, that is your p-value. The larger this p-value is, the more likely to see what you actually observed. What you actually observed is more likely to happen, so your hypothesis is more likely to be true. That's the definition of p-value. So very confusing. So I am going to skip. So here what it says is you don't need to. The idea is simply we standardize the sample mean, because we know that the standardized sample mean follows a standard normal distribution according to by the central limit theorem. So we know this distribution, so you can calculate this probability. That's what this mathematical equation says. And graphically, it's better to see from the graph. Suppose that you observe a certain one value, say 80% from the data, and then standardize your observed value or observed sample mean, and that is the t-statistic. So that must be somewhere on this line. It would be one specific value you can calculate from the data. So then suppose that this is your observation. So 80% lies here with respect to the standard normal distribution, and we are calculating probability here. If you observed 50-50 from the data, then your outcome will be here. Your actual observation will be here, and say 51-49 will be here, 52 and 53. As your outcome deviates from 50-50, it will drift away from 0 to the positive side or the negative side. So because both sides are equally likely, they are just basically the same errors, so we are treating them symmetrically. So this probability plus this probability is the p-value in two-sided hypothesis testing situation. So that's how we use the central limit theorem for hypothesis testing, and I explained it very briefly, and I hope this reminds you of the basic theory. So, however, one problem here is that we do not observe when you standardize, the mean is replaced by your belief. You believe that the mean is 50%, so it's not a problem. But the denominator, the standard deviation, is a problem because it is unknown. Usually it is unknown, but in some cases it could be calculated. But even if it is unknown, you don't need to worry. Doesn't matter, because you can estimate the sample variance in this form. The sample variance of y is an estimator for the variance. So using the estimator, you can just use the same formula. because you can show that the estimator converges in probability to the true variance. Anyhow, the idea is simple. Just plug in your estimate the denominator using the sample variance. That's not a big problem and very straightforward. What else can you do? And I am going to skip this. It is the same thing. By the way, the only thing you need to understand here is this name. It is called the t-statistic. So y bar is the sample mean you observe and subtract your belief, the value in your belief, and standardize using your standard deviation calculated from the data. That's the t-statistic. We call this as the t-statistic, or sometimes students t-statistic. That's this term will be commonly used later. So, and then what is the link between the p-value and the significance level? So there are many. You may choose the significance level. Typical choices are 1%, 5%, or 10%. And among them, 5% is kind of the standard, and we usually relate 5% to 1.96 based on the standard normal distribution information. So that is, if the I didn't explain this. So t-statistic, intuitively speaking, to interpret this, y bar is the data, the sample average estimated from the data, and mu y0 is the value you believe the mean equals. So their difference means that the difference is the difference between what the data tells you and what you believe. What you believe and what the data imply could be different, and the more different they are, the less likely your hypothesis is true, right? So and the difference measures the distance between your belief and the actual observation, and standardize the difference by standard deviation. And then if you look at this, if you think about this inequality, the standardized difference between your belief and the data is too large. Too large means larger than 1.96. Then your belief and the data are too much different. So your belief is wrong. The data will not lie, so that means your hypothesis is likely wrong. And the threshold is 1.96, which is implied by a significance level of 5%. So there are mathematics, algebra behind it, but I am going to skip that. So the important point here is this number. So sometimes, so later you are going to see a lot of p-values and a lot of t-statistics. So it's important to understand what they are and how to interpret them. So I'm over time. So here there are several slides about students' t-distribution, but I have not taught this theory in my 320 because it's old school, it's outdated, and already we know how to handle the hypothesis testing and estimator using normal distribution approximation. So I don't think it's important at all, so I will skip that. But just in case, if you have learned t-distribution based theory, you may want to read through those comments. I won't do it. It's quite complicated. I don't think it's worth. So, okay, basic idea is, in the end, simply speaking, the conclusion is, for sample size greater than 30, t-distribution can be approximated by a standard normal distribution. So you don't need to use the t-distribution, or the computers will calculate that for you. So in your in theoretical derivation, normal distribution is enough and easier to understand. So that's the basic idea. Okay, in the next video, I'm going to discuss the confidence intervals. See you.